Hi, welcome to Problem Solving Experts. In previous videos, we have established our baseline performance, we have defined how big is the problem, our sigma value, and our performance objectives. But we have established that when we are having a continuous quantitative variable metric. But what about if we cannot measure something quantitative, but we are measuring, well, actually observing defects, attributes. So it is pass or fail, defect or not defect. If that is the case, we are not having numbers, and then, well, basically we have to count proportion of defects or percentage of defective parts, or actually today we are going to talk about DPMO, defects per million of opportunities. So again, this video will be about baseline performance, how big is the problem, how big is our sigma value, and performance objectives. When can we state that we have finished our improvement? But when we are having attributes or discrete metric. So, well, let me introduce this with this example. Let's say that I have 15 parts, and here we are having the number of defects that each part is having. Some of the parts are not having a defect, some are having one defect, and some parts can have up to 4 defects. So how to calculate our baseline performance if I'm having this data? Well, we have several metrics. For instance, one of the metrics is DPMU, defects per unit. And well, basically is measure the number of defects that we are having, defects, and divided by the number of units that we are having, and that's it. In this example, we are having 1, 4, 6, 10, 11 defects out of 15 units. Okay, let's do calculation. Okay, so we are having 0.73 defects per unit. Other metric that we can establish, and in fact I like it better, is instead of DPU we can have DPO, defects per opportunities. Well, in this case we are having the definition of defects divided by units times opportunities per unit. In other words, we are having defects divided by total number of opportunities. And the question is, how many opportunities per unit? How many defects can one part have? Well, we have to talk about about establishing opportunities per unit. How to establish opportunities per unit? Here I'm assuming that we are counting different type of characteristics or different type of defects that we can measure in one part. And the question is, how many defects different defects, or how many different type of defects can one part have? Of course, the more opportunities per unit we are having, the smaller the DPO will be. And that would mean that we are having a better performance. So we have to establish very well what is the criteria in terms of opportunities per unit, because otherwise we can skew the performance just adding more opportunities per unit, and in that way we will be reducing the DPO. So to establish how many opportunities one unit can have, one part can have, let's use this criteria. So let me explain that we are having active opportunities and passive opportunities. The opportunities are the things that we measure. If we measure, we are having defects that we are measuring, we are going to call them active opportunities. If we are having defects that we are not measuring, that we are not evaluating, we are not assessing, we are going to call them passive opportunities. By the other hand, we also have active defects and passive defects. The defects are defects that are being presented. If we have had those defects, we will call them active defects. If those defects have not been had in the last 6 months, let's say, we are going to call them passive defects. So depending on the combination that we are having, we are going to count them if we are having characteristics that we measure and characteristics that are happening, defects that are happening. If we are having characteristics that are happening, defects that are happening, but we are not measuring those characteristics, then we are going to add only one as all other. And if we are having something that we measure, but we have not had those type of defects, we are not going to count them until they happen. And if we are not measuring something and that thing is not happening either, that defect is not happening either, then we are not going to count them at all. So let me give this example just to clarify a little bit better this matrix that we are having here. Let me say that I am measuring characteristics A, B, C, D, E, and F for a certain product. And I have had complaints, customer complaints, about characteristics A, B, C, D, G, H, I. Okay, so how many opportunities per unit should we have? Well, let me do that. First, let's see how many active opportunities with active defects we are having. And the active opportunities with active defects that we are having are this one. This is something that I measure and something that is happening. So this is one active opportunity with active defect. B also is something that is happening and I measure. C is something that is happening and I measure. And D is something that is happening and I measure. So how many opportunities per unit should we have? Well, let me do that. Opportunities per unit. From the active and active, we are having 1, 2, 3, 4 of them. But, question, are we having passive opportunities and active defects? And the answer is yes, we are. We are having defects that are happening, but we are not measuring those characteristics. Those are these ones. We are having a complaint about characteristic G, H, and I. We are having three different characteristics that are happening. We are having complaints, but we are not measuring those characteristics. So we are having three characteristics here. How many opportunities per unit should I add? We should not add 3, but as you can read here, add 1 as all other. Then we are going to add 1 here. Well, the next one will be how many active opportunities with passive defects. Things that we are measuring, but the customer has not complained about those. Well, we are having E is something that I measure, a characteristic that I measure, but I haven't had any customer complaint regarding to that characteristic during the last 6 months. And also I'm having F, which is a defect that is happening, that I am measuring, but is not happening. So I'm having 2 of them. How many opportunities per unit should I add? And the answer is 0. None. Reason of that? Well, so those are things that in reality are not happening. So it is very common that if we want to increase the opportunities per unit in order to reduce the DPMO, what people try to do sometimes, well, they are cheating actually, or they want to cheat, is to measure more different characteristics regardless if those defects are happening or had happened during the last 6 months. So the answer is no. Do not add any thing there. And of course, things that we are not measuring and things that are not happening, do not count them there. So that is how you have to decide how many opportunities per unit we should count or we should take in consideration to establish our performance. Because I'm not having, for this specific example, the details about what are these defects for. Is this because a dimensional problem? Is this because physical, density or strength or tension characteristic? Is this because scratches, because of dirt, or I don't have the details. But if I don't have the details, what I will do is that I will take the biggest as the opportunities per unit, the maximum opportunities per unit that one part can have. And so, for this example, then I will establish that DPO is equal to number of defects, 11. Number of units, so we are having 15 units. How many opportunities per unit? I have said 4 opportunities per unit. And that leads to 11 defects divided by 60 total of opportunities. So, let's do calculations. Okay, then our DPO, defects per opportunities, is 0.1833 defects per opportunity. That is a good way to establish the performance, but the most common, the most typical way to express the performance is in terms of defects per million of opportunities. So, let me explain then that. Defects per million of opportunities is equal to defects divided by units times opportunities per unit times 1 million. In other words, defects per million of opportunities is equal to defects per opportunity times 1 million. For the example that we are having here, then DPMO would be something like 0.18333 times 1 million. So DPMO is equal to 183,333 defects per million of opportunities. We have our baseline performance if this is our baseline data, our data before starting an improvement project. But we have not answered to the question, how big is the problem? And because in order to answer to the question, how big is the problem, we have to calculate our sigma performance. Keep in mind what I have said in previous videos. If our sigma is smaller than 2, we are having a very big problem. If the sigma is between 2 and 3, we are having a big problem. 3 to 4, medium-sized problem. 4 to 5, a small problem. More than 5, we are not having a problem. Then we have to calculate our performance in terms of sigma, not in terms of DPMO. But it is easy to convert that into a sigma value. All what we have to do is to take a look to the normal distribution areas, the table, Z table, for the normal distribution, and look for 183,333 defects per million. And from there we are going to get the Z value. And that value we are going to call it Z bench. Okay, let's take a look to the table. Taking a look to the table and looking for the value of 183,333, we can see that the closest value is 184,060. That leads to a Z value of 0.90. Okay, then Z bench 0.90. To get the sigma value, sigma value also I have said this in previous videos, is z-bench plus 1.5. Then for this case, 0.9 plus 1.5, that's equal to 2.4 sigma. This is our baseline performance, 2.4 sigma. Because the sigma is between 2 and 3, we are having a big problem. And with that, we would have our baseline performance in terms of DPMO and in terms of sigma. Basically that's it. But there are different additional things, different notes that I have to add here. One of them is, although it is highly recommended that we measure number of defects that one part can have, because one part can fail because of different reasons, can have different type of defects, in reality, most of the companies that I have worked with, and I have worked maybe in 80, 100 companies around the world, 20 different countries during the last 25 years, I have realized that most of them, I don't want to say all of them, but almost all, do not measure number of defects per unit, but they do measure defective parts. So, well, maybe one part is having 3 different type of defects, and they just call it bad part. One defect, bad part. 2 defects, bad parts. Instead of counting defects, they just do good or bad, pass or fail part. So they are actually not measuring defects, but they are measuring defective parts. So if that is the case, then still we call it DPMO, defects per million of opportunities. To me, in reality, they are not measuring defect per million of opportunities, but they are measuring defect per millions of units. And that's the way we should call DPU, defects per unit, or defects per million of units, DPMU. That's actually what they do. If that is the case, how many should be our DPU here, our defective parts, defective per million of units? Well, let's do this example to calculate DPMO, quoted, but instead of counting defects, counting defective parts. Okay, let's do that. And let me do a small space here, establish a space here, in order to calculate that. So, instead of defects, I'm going to call it defective part. So for defective part, we are saying good, defective, good, defective, good, defective, good, defective parts. In reality, what we should measure is defects, defective parts per million of units, which is defective parts divided by units times 1 million. So the defective per million of units is equal to 1, 2, 3, 4, 5 defective parts out of 15 parts times 1 million. And that is defects per million of units equal to 333,333. Okay, now let's get the sigma value. And same thing, we have to take a look to the table, to the z value for the normal distribution. Okay, if we take a look to the table and we are looking for 333,333, we can see that the closest value is 333,598. That leads to a z value of 0.43. Okay, z bench 0.43. To get the sigma value, same definition, sigma value is equal to 0.43 plus 1.5. That is a sigma of 1.93 sigma. And that would be our baseline performance. Because the sigma is smaller than 2, that means that we are having a very big problem. Well, I just want to highlight that in reality we are measuring defective per million of units. But most of the cases, companies report this performance as DPMO. In reality, again, as I have said, they are not measuring defects, but they are measuring defective parts. But well, that's a common situation, so we have to be aware when we are told this is our performance in terms of DPMO, and they are going to give us maybe defective per million of units. In other cases, they call it PPMs, parts per million. Well, what I have used is that PPMs is used for continuous quantitative metrics and DPMO is used for attribute type of data. Okay, now let's take a look to other situations where we are measuring DPMO. Well, I have said in previous videos that if your metric is a quantitative variable, a continuous metric, then you have to calculate PPMs. And basically the PPMs is the probability of having defects, and the way to calculate that probability is through the calculation of the proportions of the areas below the distribution that are outside the specification limits. But sometimes your data is not meeting all the requirements to become a representative sample. And if that is the case, then it's not accurate, it's not correct to calculate PPMs and to try to establish a distribution and so on and so forth, because again, your sample maybe is not meeting all the requirements, the characteristics necessary to be reliable. To create a distribution and calculate areas and all of that. If that is the case, then even if you are having a continuous data, a quantitative variable metric, then you have to calculate your performance in terms of DPMO, defects per million of opportunities. Let's take a look to this example. We are having sleep time per night in terms of how many hours I sleep per night. But unfortunately, at least two characteristics are not met for this data. One of them is resolution. We are not having a good resolution because, as you can see, we are having only values of 0 and 0.5. So you have 6.5, 5.5, 6.0, 7.0. So you can see you are having several 7s, you are having several 8s. That means that the data is not sensitive to perceive the variability, so resolution is not good. Second one, the sample size. Very likely, I haven't done the analysis there, but very likely the sample size is not big enough to become representative. So what do we do? Well, of course, we are having two options. One option is to change the way we measure the data, measure in a more reliable way. For instance, I can use my Fitbit and to measure with more accurately the number of hours I'm sleeping per night. But also I will need to collect more data, and maybe I am in a rush, I'm in a hurry to start improving my process. And I don't want just to wait doing nothing until I have a representative sample. So what do? Well, we can calculate, we can establish our baseline performance in terms of defects per million of opportunities. In reality, again, I will be measuring defectives per million of units, but again, let me call it DPMO. For this example, then, well, let me establish that. Defects per million of opportunities. Again, maybe they are not opportunities. Let me just call it defects or defective per million. How many defective parts are we having? Well, in this case, well, we are having, keep in mind that, so we are having defective, and here we are having units times 1 million. How many defective parts am I having? Well, these are the specification limits. The lower specification limits, the minimum I should sleep, 7 hours of sleep per night. The upper specification limit, the maximum I should sleep, 9 hours per night. And the target is 8 hours per night. So how many defectives do I have? How many defects do I have? Of course, this is smaller than 7, smaller than 7, smaller than 7. This is bigger than 9, and this is smaller than 7, smaller than 7. So total number of defectives or defects, 1, 2, 3, 4, 5, 6. So defects per million is equal to 6 defects per million. And how many units? Total number of units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we are having 15 parts times 1 million. That is 2 divided by 5, and well, that is times 1 million. $400,000 parts per million. And that's how we will be calculating our performance, our baseline performance, even if we are having a quantitative variable metric, but if our sample is not a good sample because not, in this example, not big enough or not good resolution or both, etc. By the way, I encourage you to take a look to my video regarding calculating, well, establishing or evaluating the representativeness of a sample. Then you can calculate your performance in terms of defects per million. Let's take a look to another application of defects per million. Okay, other application of defects per million, and that is calculate the actual performance in terms of defects per million, but when we have calculated our performance in terms of PPMs, but we have excluded the outliers from the PPMs calculation. What I have said is that in order to get a distribution, well, what you have to do is to identify if there are special causes of variation. We are calling to those special causes of variation, and subtract those outliers from there in order to avoid or prevent to skew the distribution and not having a representative distribution of your actual population. So you have eliminated your outliers from your PPM calculation, but those outliers that you have removed from your data should not be ignored, because those outliers were real. If they did happen in the process, well, that's part of the performance of the process. Then, yes, you have your PPM, you have your sigma, and those are what I call the natural PPMs, the natural sigma, but you have removed your outliers. Now, what you have to do now is to adjust those natural PPMs, including the outliers, to calculate your actual performance and your actual sigma. To calculate that actual performance, we are going to calculate that actual performance in terms of defects per million. So, let's say that we are having a baseline. You have a quantitative variable metric. You have calculated your PPMs for a normal distribution or whatever the distribution it was, and your performance was 64,520 PPMs. And also you have 40 values, and those are values without outliers because you have removed the outliers from your sample. Well, number of outliers in the original data that you have, well, you had 2 outliers which were inside the specification limits and 8 outliers that were outside the specification limit. Keep in mind, an outlier is a value that is very different than the rest, but it can be inside the specs or it can be outside the specs. If identified as a special cause, you have a special cause that you can assign. Doesn't matter if it's inside the specs, it is an outlier. So, well, let's say that we had 2 outliers inside the specs and 8 outliers outside the spec. So what is your actual performance? Your actual performance is not 64,520 ppms because you have ignored those outliers that really did happen in the process. So what you have to do is to adjust your performance, and then you will be calculating the defects per million adjusted. And those defects per million adjusted will be the natural defects, and those are the defects coming from these PPMs that you calculated without the outliers, plus the defects because special causes of variation. The special causes of variation. And then divided by total number of units. Total number of units. Let's do that calculation step by step. First, how do I get the natural defects? Well, we are going to convert from a probability, from PPMs, into defects per million. And then we are going to calculate defects, how many defects we are having. So here, our performance, we are having that, the number of defects that we are having in certain number of units that we are having. So for this example, we are having 64,520 defects in 1 million of units. That is our performance. But in reality, we didn't have 1 million units. What we had, without outliers, were 40 units. Then the question is, in 40 units, how many defects are we having? Okay, let's calculate those natural defects. I will call to that one natural defects. And well, how many would be those natural defects? Which is basically 40 times 64,520 divided by 1 million. And the total number of defects, natural defects, are, okay, we are having the natural defects, 2.58 defects. That means that in 1 million we are expecting to have 64,520 defects. Because we are having 40 values, well, we are expecting to have 2.58 defects in 40 values. Well, and those will be our natural defects. Now we are ready to calculate our performance in terms of defects per million, but including the outliers. So the defects per million adjusted are natural number of defects, 2.5808, and those are the defects that we are expecting to have in 40 units. Plus defects because special causes of variation. Those are the outliers that are outside the specs. Outliers outside the specs. Well, we are having 8 outliers outside the specs. Divided by total number of units. What was the sample size for the original sample that we had? Well, the original sample was 40 units, which are without outliers, plus 8 outliers outside the specs, plus 2 outliers inside the specs. And all of that times 1 million. Then the defects per million adjusted is equal to 10.5808 divided by 50 times 1 million. Defects per million adjusted are equal to, let's do calculations. And as you can see, our actual performance is 211,616. That is a very different performance, very different than the original performance that we are having here. So we are having maybe 3 times bigger in the amount of defects. So it's really different, this performance. So if we ignore the outliers, the apparent performance ignoring the outliers can be pretty much better than the actual performance if we take in consideration the outliers. If the outliers are real, we should not ignore the outliers, but you should, yes, we have to remove in order to have an accurate calculation for the natural PPMs, but later we have to adjust, and then this is what we can do. Well, by the way, this is the total formula, number of values without outliers times PPMs without outliers divided by 1 million, and that will lead to the natural defects, plus outliers outside the specs, 8, divided by number of the values without outliers, 40, plus outliers outside the specs, 8, plus outliers inside the specs, which are 2 times 1 million. And well, basically that will be another application. Let's take a look to one more application of defects per million. Well, this other application about defects per million, I have talked already about that one when I was talking about type of statistical problem, and basically that is when we were calculating Z control to identify if we are having a lack of control or lack of attention to the process problem. But well, I will repeat that because this is part of the subject, defects per million. As I have said, for continuous quantitative values, most of the cases we may have a normal distribution, and if we are having a normal distribution, the natural variation will be the mean plus minus 3 standard deviations. So well, basically here you can have the mean plus 3 standard deviations and the mean minus 3 standard deviations. And those will be the upper control limit and the lower control limit. And that variation we call the natural variation. The area below a normal distribution is 99.73%. So we still may have some values that be outside box whisker limits, and perhaps they are not, there is not a special cost associated to that, because that is part of the normal distribution, that is part of the natural variation of the process, because still the probability of having values outside those control limits is 0.27%. So the question is, okay, not because we are having one outlier that means that we are having a control problem. It depends on how many outliers, because again we are expecting to have 0.27% of potential outliers. They are not outliers until we find the special cause that we can assign to that one. But well, anyways, so here in this example, I'm having 4 outliers. So we are having 4 values that are outside the box whisker limits. I have talked about that when talking about representativeness of data for a sample. So let's say that the specification limits are here. Let me say that here we are having a lower specification limit, and here we are having an upper specification limit, just to establish something. So we are having one outlier inside the specification limits, and here we are having, well, let me add one more, let me add another one here. Here I'm having three outliers outside the specification limits. So the question is, are they many outliers or are they an acceptable amount of outliers? Well, assuming that we have not assigned special cause yet, so they are potential causes of variation. Well, let's calculate our Z control value. In order to calculate our Z control, what we have to do is to calculate defects per million for outliers. And as I have said, it is a number of outliers inside the specs plus number of outliers outside the specs outside the specifications divided by total number of values without outliers plus outliers inside the specs plus outliers outside the specs times 1 million. So our defects per million in terms of outliers are, take a look, for outliers it doesn't matter if the outliers is inside the specs. The hypothesis is that we lost control of the process, and then because of that we are having a special cause, and that is a defect in terms of control of the process. Maybe not to the eyes of the customer, because to the eyes of the customer we are inside the specs, but in terms of process control we are having a defect because we lost control, because that's a special cause. So okay, defects per million, outliers inside the specs 1. Plus outliers outside the specs 3 times number of values without outliers 120 plus outliers inside the specs 1 plus outliers outside the specs 3, and that is equal to 4 divided by 124 times 1 million. So the defects per million because of outliers is equal to, let's do the calculations. Okay, then the defects per million for outliers is 32,258. And is that acceptable or not? Well, we want to get now the Z control value. The Z control, basically what we have to do is to look for the normal distribution, Z value, and look for this area. And for that area, the Z value will be this, what we call the Z control. Let's take a look to the tables. Taking a look to the table and looking for value 32,258, we can see that the closest value is 32,157, and that corresponds to a Z value of 1.85. Okay, Z control 1.85, and well, what is the meaning of that? What we have said is, previous video again, is that if Z control is smaller than 1.5, we are having a control problem. We are having many outliers, and what we have to improve the attention to the process. Maybe visual management is a good idea. If our Z control is greater than 2.5, we don't have a problem. The amount of outliers that we are having can be part of the normal distribution. But in this case, we are in the middle. So we are not green, we are not red, but we are yellow. And that means that the Z control is between 1.5 and 2.5. So we are not having a control problem, but we have to improve our control. It's still not a problem, but warning, we are getting close to have a control problem, so we have to improve. And well, basically with that, we are finishing the calculation of baseline performance and different applications of DPMO. Now I would like to talk about performance objectives for DPMO. In a previous video, I have talked about how to establish performance objectives for PPMs when you are having a continuous quantitative metric. Well, but what about if you are having attributes, if you are having DPMO? How to establish the performance objectives for DPMO? Well, the concept is exactly the same, and I would say the same mechanics, very similar. So there are the most typical ways to establish performance objectives, as I have said in a previous video, are benchmark, which is compare to the best with the best, which, by the way, that is the method that I recommend the most. Requirements from the customer, requirements from the headquarters, requirements from the government regulations, etc., demands. Entitlement, especially when we are having a Z control problem, the objective is to remove all the outliers and then all the special causes of variation, all the shift as well. And well, in another video I will talk about entitlement. And rule of thumb. Also, what I have said is that if your baseline performance is smaller than 3 sigma, our objective should be to reduce defects by 70%. And also, I have said that if your sigma baseline is greater than 3 sigma, then you have to reduce defects by 90%. As I have explained in another video, this is not coming from any theorem, from any calculation, but this is just basically experience from a big database in 20 years of experience. So, for this, taking this, let's calculate our performance objectives using the rule of thumb. So, if my baseline performance is 3.3, then I have to remove defects by 90% because it's greater than 3 sigma. Then I will eliminate 90% of the defects, and my new performance will be 10% of those defects. So, in this case, the DPMO is 10% of that, which is 3,593 defects per million, and that will be my performance objectives. How much is that in terms of sigma? Well, let's do the same. Take a look to the normal distribution tables, Z value, and look for the Z bench value. Let's take a look to the tables. Taking a look to Z table and looking for value 3,593, we can see that closest value is 3,573. That leads to a Z value of 2.69. Then Z bench is 2.69. Okay, so Z bench 2.69. Then our sigma value or sigma level is equal to Z bench plus 1.5. Then our sigma is 2.69 plus 1.5, and that is equal to 4.19 sigma. 4.19 sigma. Then our objective is 4.19 sigma. So we want to improve our performance from a 3.3 sigma to 4.19 sigma. Same thing of what I have said in a video regarding performance objectives when you are using PPMs or a quantitative metric, which is, it doesn't matter what method you are using to establish your baseline performance. Your goal, your objective has to be outside confidence intervals. Otherwise, we cannot state that that is a significant improvement, a significant change. So then we have to evaluate our confidence interval. This 3,593 is outside confidence interval. Then let's calculate the confidence interval. The confidence interval can be calculated with this formula. And this P is the proportion of defects, which basically means defects per unit. Or defects per opportunities, but in this case we are not talking about defects, but we're talking about defective, so defective per units. So for this case, well, then we can establish that. We can establish that P, for this case, is going to be defects per units. It can be also defects per opportunities. In this case, well, is defects per million, which is this one, defects per million, divided by 1 million. And that is equal to 0.03593. Okay, so we have our defects per unit, or defective units, which is P. Z value, which is from the normal distribution, 95% confidence level, alpha of 5%. The value from table for Z is 1.96. As I have said, I encourage you to take a look to my previous video regarding to confidence intervals for quantitative data, and I'm talking about confidence level, the effect of sample size, and all of that in the confidence interval. And so, well, and N, which is the sample size, 350. First, I want to calculate this term. I won't be calculating everything, but I will be calculating the term that is subtracting and is adding to the defects per unit. Z value for alpha divided by 2 is Z 0.05 divided by 2, the square root of defects per unit, 1 minus defect per unit divided by sample size. Well, that value is equal to Z 1.96 times square root of P, which is 0.03593 times 1 minus P, 1 minus 0.03593, and all of that divided by N, which is the sample size, 350 parts. Okay, let's do the calculations. Okay, then this term is equal to 0.009948. Then we are ready to calculate the confidence interval. And the confidence interval is P, which is defects per unit, 0.03593. Minus this term, which is 0.009948, smaller equal than defects per opportunities, smaller equal than 0.03593 plus 0.009948, which is this value, this plus this. Okay, then let's do calculations. Okay, we are having the confidence interval for defects per opportunities. If we multiply each of the terms times 1 million, we are having the defects per million. So our confidence interval for defects per million would be 25,982 smaller equal defects per million smaller equal than 45,878, and that is our confidence interval. So we have taken a sample size 350, and from that sample we have calculated defects per million of 35,930. But if we take another sample, we are going to get another defects per million, and if we take other sample, we will get other defects per million. So what is the defects per million of the population, the actual defects per million? Not the defects per million for one specific sample, but the defects per million of the entire population. And the answer is, I don't know. But with 95% confidence level, I can tell you that the defects per million of the population can be somewhere, very likely will be somewhere between 25,982 defects per million and 45,878 defects per million. So that is where the defects per million of the population, very likely with 95% confidence level, will be. Now, what I have said is that the objective, the performance objective, has to be outside confidence interval. My performance objective is 3,593 because this value is smaller, much smaller than 25,982. That means that it is outside confidence interval. So that is a significant change. That is a valid objective, and then we can go ahead and then we have established with that the baseline performance and performance objectives. Okay, well, that's it for today. Next video, I'm going to talk about calculating Z values, Z shift, Z short term, Z control, different type of problems, but when we are having attributes. I have said that, I have another video for when you are having a quantitative metric, but not for attributes. Well, thank you very much. I appreciate your attention.